Hi, everyone. Thank you for coming. Today we have Roberto Cominneti. He's a professor at Universidad Adolfo Ibáñez, and he has worked on optimization, transportation problems, games. And well, we're happy to have him. He's staying for 2 weeks until this Saturday, so he'll be leaving soon. But of course, if you want to contact him, he's more than happy to answer questions now or later on.
So thank you very much first to Daniel and all the team for the very nice reception here. And last night was great, the dinner. And so I am planning to talk about this topic, which is the subject of a recent paper. So it just came out a couple of months ago in Science Journal Control Optimization. It has to do with the control of Markov's decision processes. So my plan, I should say that this is joint work with a colleague in Santiago, Mario Bravo. So the paper is available. If anyone is interested, I can give you the reprint. So that will be my program. Basically, I will focus on the three first topics and go quickly over the fourth. So I will start by describing roughly what is the problem I'm facing. This is very basic. I'm not pretending to do a survey of Markov decision process. That would be a huge topic. So I will just give you the more narrow problem that we're interested in, and I will explain why this case is has some peculiarities that make it a bit challenging. And then to address this problem, I will look at one particular iterative scheme for mean-payoff MDPs and establish the connection with these Krasnoselski Mann iterations, which are basically fixed point iterations for maps that are only non-expansive. So there are no construction, only non-expansive. And it turns out that the solution of the Markov decision process in mean-payoff requires exactly this type of problems. Once I survey what we know about these Krasnoselski Mann iterations and the techniques we have to analyze that, I will go back to Q-learning, which is the algorithm for mean-payoff MDPs, and explain what we obtained. So in terms of results that we expect to have, there are two of them. On the one hand, we will propose or we will analyze this Q-learning procedure. We would like to prove that this procedure converges to the solution of one of MDPs. But beyond that, we would like to know what is the speed of convergence of the iterates toward the limit. And even more importantly for us will be to provide finite time error bounds. So after k iterations of the algorithm, I would like to have an estimate of the expected error that and hopefully the most explicitly possible. And then as a byproduct of the Krasnoselski iterations, I will describe what it gives you when you study stochastic gradient descent and more generally the case of stochastic iterations with bounded variances. But this depends on how much time we are left. By the way, any questions, please feel free to interrupt anytime. So let me start by setting the stage. This is a sort of introduction for what comes later about mean-payoff. So imagine that you have a stochastic system, a system that moves stochastically, and it's described by a Markov chain. So you have some transition probability, you have finite set of states, which will denote S, and when moving from I to J, so I will be the initial state, J will represent the final state, you have certain probability. But on top of that, you can control these probabilities by this action A. Everything will be assumed finite in this talk. So you have a way to decide, if I'm at state I, what is the best action that will lead me to a next state J, which is in some sense desirable. And desirability is controlled by this reward. In general, it's a function of the initial state, of the action you're taking, and the final state that you reach. It could depend on everything, or it could depend only on one of those. The example will only depend on the final state, the state that you attain, J. So once you have that, if you're given an initial state, let's say it's deterministic, you know exactly where your system starts from. This is I0. And if you prescribe a sequence of actions, AT, well, you have a Markov chain that will evolve according to this transition probability. So the next state, t plus 1, t will be the epoch or time. So at stage t plus 1, your new state will be selected according to these conditional probabilities over the state of states, which depends on your current state, IT, and your action. What is the goal? Well, I would like to prescribe or to find out a stationary policy. What is a policy? Is a map that, given a state, tells you what to do in that state. So it assigns to each state an action. And I would like to choose this policy mu so that this control, by choosing systematically AT just as a function of the current state IT, to minimize the long-run expected average payoff. So you see, once I have controls, I have a stream of payoffs, one for each stage. And how do I there are different ways to evaluate a stream of payoff. One possibility is to use discounting. So I discount with a certain rate. Future rewards are discounted to bring it, which makes a lot of sense when you're talking about money. But in some applications, especially in systems that run continuously, suppose that, you know, R of t is some measurement of a system which is which are doing maintenance. Well, maybe in maintenance you only want the things to be running smoothly in the long run. Well, this type of object is not discounting the objective function, but what you do is you consider the long-term average, 1 over t, the sum of the, so you look at the long-term mean payoff over per period. And of course, this is stochastic, so you take the expectation. And then you look at the limit when t is large. Again, you add up, you compute your average payoff per period. You take the expected value in the long run. That's what we want to optimize. And okay, I'm basically following here a classical reference, which is there, Puterman, where it discusses a lot of applications in maintenance, in telecommunications, or control of queuing networks. There are many, many applications. I will not give you any general examples. I wouldn't be able. I would rather present a very small motivation example, the minimal example. So suppose that I have only 2 states and 2 actions. And suppose, moreover, that the rewards depend only on the final state. So I have 2 states. On state 1, my reward is 1. So when I'm saying at this state 1 here, I get a reward of 1. If I'm at state 2, I get a reward of 10. Of course, if I'm maximizing the average payoff, I would like to be at state 2 as often as possible. Now, the transition probability depends on your action. If your action is A1 and you're standing at 1, well, you stay there with probability 0.3. You move to the good state with probability 0.7. If you play action 2, well, you stay with high probability at state 1, and only 0, 1 to move to the good state. So that's clear that if I'm at state 1, I should favor action A1. And vice versa. At state 2, I want to stay at that state with action 1. I stay only with probability 0.3. With action 2 is much higher. So the optimal policy would be play A1 at 1, play A2 at 2. And if you look at the long-term average reward and so on and so forth, you get that the value, the optimal long-run average, and this is the optimal, it can be proved that this is the optimal, is 71/8 in this example. Okay? So what we're looking is at those type of problem. So this was very easy, but now imagine that in the same example, I don't show you the probabilities. And I don't show you the payoffs. I don't show you anything. The only thing I give you is that when you try one action, I sample from the true distribution the next state, and I show you the next state. But I don't tell you with which probability I chose. So you cannot compute this objective function. You can only observe what is the next state and what is the reward that you get in that stage. So you observe your current state, you observe your action because you choose one, and then you observe the next state and the reward. But I'm hiding everything else. The question is, so I don't know P nor R in advance, but I can possibly learn along the way. And that's a question. Can we come up with a method that adaptively learns an optimal policy? That's the main issue. So I will start going a bit quicker. There's some technical assumption here, which is, believe me, quite mild. I'm assuming that every time I get a stationary, I prescribe a stationary policy, while the induced Markov chain is unichain. That means that there is a unique stationary distribution. Well, in that case, the large R mu I0, remember, is just the long-term expected average payoff. This value doesn't depend on the initial state, and that's quite expected, right? I'm just looking at the long run, it doesn't matter. There is a unique limit stationary law distribution. So the initial state shouldn't play any role. So from that point of view, I0 is irrelevant, but of course it depends on what policy mu I'm taking because the stationary distribution will depend on that. Well, it turns out that the optimal value, R bar, which is the minimum of our mu overall mu, and the optimal policy can be obtained by solving this type of Bellman's equation. And here's the fixed point formulation of the problem. So I'm looking in this problem, I'm looking for a vector V indexed by states. It's called the relative value for every state, and which satisfy this set of equations where you have V on the right-hand side and V comes over here. So V of I is just the maximum overall actions of the expected value. I'm taking the expected value with the transition probability when I fix A of the reward plus Vj minus R bar. So I should solve this equation. It's an equation in V, except that already to state this problem, I should know R bar, the optimal value, which is not known, unfortunately. And we will come later to that. But if by any chance we know R bar, then we only have to solve this problem. And this is a fixed point equation, V equals some TR of V, or I think I will call it H. What you see in the right-hand side is an operator which acts on vector V. And this operator, you can see that it is monotone. If I increase V, it will give me something bigger. And if I add a constant, the constant comes out. That's called isotone. And this implies that this operator is non-expansive in the L infinity norm, the norm infinity. So you're computing, you need to compute a fixed point of a non-expansive map with respect to a very specific norm, which is the norm infinity. The solution is never unique because you add a constant on both sides, you add a constant to V, and you have another solution. But basically, that's the only source of non-uniqueness. Besides that, this equation has a unique solution up to a constant. The problem is that R bar, I don't know a priori. I could try to adjust it, right? Well, that doesn't work. I could try to guess what R bar is and solve for V and then try to move, adjust. Well, that doesn't work because it turns out that this equation, if it has a solutions, then R bar should be the optimal value. If you miss by epsilon, this equation has no solution. It's if and only if. So you really have to plug there the exact optimal value R bar, which is not known. It's not exact. That's a big issue. So you have some fixed point theory, a fixed point problem of an operator that you cannot compute because you don't know R bar and you don't know P. And you don't know R. So you know nothing, and you want to compute a fixed point. And you really have to plug there the R bar, which is exact, otherwise there is no solution. And the operator has some nice properties, non-expansive, but still is non-expansive in a nasty norm. It's not a Euclidean norm. And most of fixed point theory works for good norms, for Euclidean norms. Here's not the case. You have norm infinity. Well, let me rewrite this equation by calling this Q factor. So all the expression that it is inside the blue expression, let's call it Q factor. Then I can express VI in terms of the Q factors. You can rewrite this Bellman equation in terms of Q factor. So the only change is that the max operator moved inside. So I'm replacing Vj by its expression in terms of the Q factor. So that's another writing of the same equation. And again, this has a unique fixed point up to a constant, provided that R bar is exactly the optimal solution. Otherwise, there is no fixed point. So this is the form we will address. So here's what I just said. This is a fixed point for a map H, which is just an expectation. You see, I'm taking the sum over all possible future states according to probability P. So I'm taking the expectation with respect to the next stage of the reward, the immediate reward, plus some sort of future reward, except that I have to remove this R bar here. This map is non-expansive, as I said, in norm infinity. It has a unique fixed point up to a constant, but it might be difficult or even impossible to evaluate because of one, the R bar is typically unknown. And for a fix, what I will do is that in the iterations, instead of computing a fixed point for for the wrong R bar, I will iterate I will replace the R bar by a function of the state. And this is not our idea. This is Abunadi-Bertsekas that proposed in the 80s to do this trick. So we replace R bar with a function of f of q. I will tell you what function you should choose there. And consider this new operator H star. Now I can evaluate, except that I don't know how to compute the expectation, know the reward. So I can replace the expectation by some sequence of samples and try to do something with that. That's the only information we get stage after stage. Well, if you do that, then here's what Q-learning proposed by Bertsekas and Borka. You say, let's suppose that I have Qn minus 1, an estimate of the fixed point I'm looking for. I observe the next state and the reward, and I replace the expectation by this sampling of the operator. And with this, by a simple averaging, 1 minus alpha n, the previous iterate, plus alpha n, this part, which is just a sample of the operator. There is no expectation, but it's just a sample. I do the averaging, and I take this Qn as my new estimate of the fixed point. And this iteration, xqn is a matrix, which is indexed by state I and action A. So this is what is called tabular RVI Q-learning. It says that for every I and A, I update this value. So I take independent samples, and what I'm requiring from F for technical reason is very simple. It's simply that it is homogeneous with respect to adding of a constant. If I do that, then it turns that this H star, now it has a unique fixed point. Unique, not unique up to a constant. So somehow the f of q will fix the constant. So it has a unique fixed point. And in fact, it will be the only element of fixed h, which was unique up to a constant, which interpolates such that f of q star gives me exactly the optimal value. What I lose is that this f of q is no longer non-expansive, just because I added this function f of q. But this will not be a problem. Examples of such functions, well, take the average of the matrix, or take the maximum of any normalization. You can think of f as a normalization function. So in this case, going back to the example, if you take the maximum, the fixed point is over here. And if you look where the maximum is 71 divided by 8. That was the optimal value, 71 over 8. And this is the Q star. You fix the constant with that. So here is an example. On this example, I run RVI Q-learning. So this iteration RVI, which is there, you can simulate and run. So here are some numerical illustration. Well, you have to choose what is your update parameter alpha n. So here's, for instance, 1 over n plus 1. And here are 10 sample paths. And I'm plotting here f of qn, and as expected, you see it concentrates around r bar, which is 71 over 8. And you'll see that all trajectories converge. And in terms of expected rate, if I look at what is the fixed point residual, what is the error for the true operator h, which I cannot compute, but still, this expected value, it scales in this case like square root of log n. That gives you the rate of convergence. Maybe a bit faster because you see this product is still decreasing, but I can tell you that your error is roughly decaying as 1 over square root of log n. It's not very fast, but it is what it is. It seems to be pretty much tight in this example, at least.
I have a question.
Yeah.
Maybe I just missed this because I'm not paying attention, but how do you handle? Do you need to do exploration? Are you doing exploration, or is your Markov? Are you assuming that like for every policy?
If I need to do what?
Any exploration, like the
Any exploration?
So I mean, this convergence is like convergence for a fixed policy, or are you optimizing the policy as you go?
I'm just doing this iteration over there.
Okay, so you are picking the best action at each.
I'm taking the best action here.
Yes.
When I compute the maximum.
Yes.
It's a sample maximum.
But it's a sample maximum.
Yes.
So it's not a policy. I take Qn minus one was my previous estimate of the optimal policy
Yes.
of the Q factors. I observe the new state, and I do a posteriori what would be the best action starting from the next period on. So here's the current RIA, which is the reward I get immediately.
Yes.
And then I adjust my policy for the next state. I take the best policy U.
Are you assuming that all states are visited with positive probability for all policies?
Not necessarily. I only assume that if you give me any policy, any fixed stationary policy,
Yeah.
the Markov chain that results is unit chain. It has a unique,
So there could be states that are transient for that policy.
yes. And different policies could have different transit states.
Yeah. I mean, I guess if you start out with a policy that like never wants to visit some state, and then like you observing good rewards, like are you going to like under this strategy, are you going to like explore the whole space?
There is no policy here.
Um,
I'm not
Yeah.
fixing a policy.
Yeah.
And I look at the state psi IAN, so the next state you arrive, and you take the best action that you would take, assuming that your Q factors are given by Qn minus one. Eventually, if the Q converges to a Q star, the R max there will give you the optimal policy. The optimal policy will be once you have converged, where your Qn converge. So if I give you the Q star, this fixed point, then by taking any U that maximizes for this QIU or QIA maximize over A, this is the optimal policy. But in this iteration, I don't need to specify any policy. So it's not policy.
I guess here's what sorry, maybe I don't mean to dwell on this, but I just want to make sure I understand what's happening. So if you had a state action pair where there was a very rare high payoff, and usually the payoff was like bad, 0, negative, whatever,
Mhm.
and you sampled it a few times, and then you saw that it was always bad to be here, and then you ended up in a policy that like, if there was a feasible policy where that state was transient, then like you may never even observe the very high payoff because you didn't visit it enough times.
Mhm.
How do you, but if the optimal policy if the optimal policy does need that big rare payoff, are you guaranteed to, I mean, it seems like you're saying that you should get there.
You should get there. Yeah. The theorem tells you that if you choose alpha n adequately, it will converge to the optimal solution.
And
Now, if you have a state which usually gives you bad payoffs, then this Qn minus one, when you update, it will usually update, well, with the maximum of the previous one, but if they are bad, you're averaging with bad payoffs. The R, which is there, is usually very bad. You say with small probability, you get a super high payoff. Well, when that happens, when the system jumps over there, then you will get this payoff and will balance up, and it will raise the Qn, and it will raise the.
so I'm just, what ensures that we're going to continue returning to the state that had the bad payoff?
So Q is a matrix, so you're evaluating every state and every
Yes.
state and every action every time.
Yeah.
So you're forcing the iteration is saying, I'm going to pick that bad state. Because you need to evaluate Qi of A, I being the bad state, with all the actions. So you're sampling, every time you're sampling every possible transition. Right?
Yes.
Oh, it's not one sample path. Oh, okay.
No.
Sorry.
No,
I thought
no.
it was one sample path.
No.
So I mean, I'm
That's what we're currently working on.
yeah, okay.
It's online learning in
Okay.
that case. No, here is tabular. So for every I, you simulate your next state. For every I in action, you
Yep.
simulate what would happen, and then you adapt. It's a tabular.
Sorry, I had this
This idea of
addition of like I'd seen this before and then like another, and I thought that we were doing the other thing.
no,
What's the intuition of what Q is?
that's a
Because it's not the policy. it's
no,
sort of
no. Q,
information.
Q is a sort of value, but it's a relative value because you know that
Yes.
the optimal value doesn't depend on the initial state. Whereas these Q factors are sort of what small advantages give you at state I to start with. So it's a sort of first order approximation of the optimal policy, first order sensitivity with respect to the action. With respect to the initial state. Although in the long run, the initial state doesn't have any relevance, well, this gives you a sort of first order expansion. And this is why you get this R bar over there. So I have a final slide where I try to provide some intuition, but it's purely technical. I don't have a good, no.
It's weird because it's gonna matrix.
One more question, like, okay, if I have the ability to sample Q, like I can call sampling Q as much as I want. Like, I mean, is this procedure any better than like me just sampling Q, then forming the LP that solves the long run average cost problem and then solving the LP? Like, I mean, what is like, if I were to do that, what strategy should I use to sample?
Yeah, so the question is, why shouldn't I sample? I mean, there are several things that you can do. If you're allowed to sample repeatedly, you can estimate your probabilities by just doing a lot of sampling and then estimate your P a priori and then just solve for the equilibrium. There is not a big advantage, as far as I know. There's not much difference between the two.
Yep.
It's basically the same. I mean, here it's just, you don't need to solve any equations, but you just do a sort of update. It's like you were doing, you were solving the linear equations by a sort of iterative scheme.
Okay.
And then, as the process evolves, your probabilities are adjusting themselves. So it's not really different. The small advantage that I see is that this can be more easily adapted or extended, rather, and it's not trivial, to the case that you're interested in, which is the online case, where I don't have the right, so I'm at state I, I'm only allowed to take one action and observe what happens with that action. I cannot observe what if I had played a different action. Here, I'm allowed to sample for a state I, every possible action and see.
For every state
If you're controlling a system online, you're not allowed to do that. You cannot go backtrack and say, okay, what if yesterday I did something else? No, okay? But this is more challenging. We're working on that right now, but the techniques will more or less have half of the results already. Okay, so I guess I'm running already out of time.
No, I think that we have at least 15 more minutes. Sure.
Okay, so yeah, I will try to speed up. So here's another rule. I take alpha n 1 over n plus 1, so something which decays the power law. The sample paths are a bit more noisy. The rate seems to go like 1 over square root 10 of n. Really slow. What is best? Log n, square root of log n, or 1 over n square root 10 of n? You can tell me both are terrible, and I would agree. But in fact, log is better than this. This polynomial, I mean, power law. But in order to observe that this beats the log, eventually it will beat. But you need n 10 to the 9, something like this. 10 to the 9 iterations to have this square root of 10 to beat the square root log n. So it's so having a polynomial is nice, but it only works for n very, very large. No one will do that. So it's pretty useless. Well, here's the spoiler. All of this, including the 10 over there, and the square root log n, and all of this can be proved formally, and moreover with explicit error bounds. I should probably cut through Krasnoselski Mann iterations, but let me quickly give you some rough idea of how we address this problem. So I take a more general problem, which is to compute or to approximate a fixed point of an operator T operating over a finite dimensional space. And the only assumption is that T is non-expansive with some norm. And I'm assuming that T is only computable out to some random noise. So I have this stochastic Krasnoselski Mann iteration. Krasnoselski Mann iteration is when you take un equals 0. If you're interested in stochastic gradient descent, well, the operator T will be the identity minus 2 over L, the gradient of your objective function. I'm assuming that you have a convex function, which gradient is L Lipschitz, which is more or less the standard setting for stochastic gradient descent. Then you can, stochastic gradient descent is exactly this SKM iteration with an operator very specific, which is identity minus 2 over L, the gradient. In that case, the norm will be Euclidean norm. You get non-expansivity with respect to Euclidean norm. In our case, the operator T will be this H, for which you want to compute the. And here, I'm only assuming that it's non-expansive with respect to some norm. I don't ask anything special about the norm. So that's the iteration. It's a sort of successive averages. I'm averaging the previous iterate and the image, except that the image I cannot compute. I can compute it up to a noise un. What I'm studying assumption, the alpha n are averaging sequences, so it's a sequence of scalars with this property that sum of alpha k 1 minus alpha k is plus infinity. You may have seen this many times in different contexts. This condition comes up. And the noise, I'm assuming that it's a martingale difference sequence in L2, so it's essentially a centered variable with zero expectation and with bounded variance, with finite variance, sorry. So I will denote theta n, the variance of the noise. This will play a role. You have to control that one, otherwise you have in trouble. And they're assumed to be finite, but they could possibly grow with that, which is essential to study the Q-learning iteration. In the Q-learning iteration, you will have that theta n grows like log n. You can establish this type of growth. So I'm assuming the noise is finite, has finite variance, but the variance may grow. So let me just give you a very rough idea of how we can proceed. Suppose that, forget about the noise, and you have this sort of successive averages. So how can you prove that, how can you estimate the residual of your fixed point, which is a measure, the natural measure in this case of, you would stop the iteration as soon as this is small. How can you estimate that? Well, if you had contraction, that would be easy. That's Banach typical trick. This decays like a geometric series, but here you just have non-expansivity. So what do? We observe that xn is an average of the previous iteration and the previous image. I can backtrack. I can say xn minus 1 is itself an average of the previous images and so forth and so forth. And finally, you get that xn is some sort of averages along your path iterations of the object. And the pi-n's are prescribed by the alphas. And it's very explicit. Now, suppose that we can estimate the distance from xm to xn for the moment. Suppose that I have an estimate dmn. Then what happens with xn minus txn? I replace, right, the value of tn in terms of this pi. Then I do triangular inequality. I use the non-expansivity of t. I use my bound. So I get a bound for xn minus t of xn. The question is, So how can we find an estimate of the distance between two iterates, m and n? Well, we do the same, and here's where optimization comes into play. So we'll do a matching. You see, xm is an average of some vectors. Xn is also an average of some vector. Let's match those weights, those probabilities. So I take variable zin. So I assume that pi m is the blue weights are the pi im. The red is the red mass, and I will try to match those by doing an optimal transport problem. So solving a linear program, because you see, xn minus xm is just this difference. If I take z with those good properties that send a transport from pi m to pi n, I can express everything in terms of a single sum. And now let's do triangle inequality here. So if I do triangle inequality, I use non-expansivity, I get Zij, the previous iterates. If I assume that I already computed bounds for the previous iterate, I have a new bound for m and n. So the idea is to do this recursively, to use the previous bound di minus 1 j minus 1 to construct the next bound mn, and then proceed inductively. So I define my dmn as the optimal transport problem for sending pi m to pi n. And what is the cost? The transportation cost will be the distances that I estimated previously. So it seems a bit involved, all of this, because it has one advantage, is that, you see, the operator t disappeared, plays no role. This thing is just an iteration of real numbers. You take the dij minus 1, it's a double induction on m and n, but you can build that. And this has a lot of properties. This dmn turns out to be a distance. It turns out there is a greedy algorithm to compute them. You don't need to solve the linear program. I can give you a greedy procedure to compute them. And more importantly, you see, we went through all of this to find these bounds, and these bounds provide you an estimate finally for the residual you get at the nth iteration. And these DMNs, you can compute it a priori. They only depend on the alphas that you chose. Given your alpha, you compute your D, with your D, you compute your bound Rn, and you're done. You have your estimate. Independent of the operator T, independent of the space, independent of the dimension. It could even work in infinite dimensions. So the bounds you obtain here are very robust. They work for all operators. And you might say, okay, that's too much. It means that we overestimated everything. Well, no, I can construct you an operator which satisfies each and every inequality as an equality, where xm minus xn in norm is exactly equal to dmn, and your residual over here, the rn, so the norm of xn minus t of xn is equal to this rm. There is an operator which satisfies each for every nm. It satisfies everything with equality. That doesn't mean if you give me a specific operator, maybe you can do better. But it does mean that the technique, in the worst case, is the best you can expect, these values.
Maybe I missed an assumption or something. I mean, I've seen like the contractive mapping stuff before, but this is all, I've never seen this. Is there some assumption on like the boundedness of the space so that with the non-expansive mapping converges?
It comes to.
Okay.
So here is exactly this issue. For the moment, I'm assuming that my operator operates from Rn to R, or Rd to Rd.
Okay.
So here's the result, which there is an original result in Bayonne-Brook. and then we completed that in 2013. So a special case was treated in by Brook, who stated this as a conjecture, and we proved it in 2013. So let me define kappa equal 2 times the distance from x0 to fixed t. This already requires that I'm assuming that t has a fixed point. Okay? So all my iterations will live in the ball center at x0 and with this k. And in fact, the operator t is confined to that ball. Alternatively, I could take kappa if your operator t is operating from a convex bounded set into itself. I could take kappa just the diameter of that set. Okay? So that's, I think that.
Okay. Yeah, I mean, I was thinking like, like x to x plus 1 is a non-expansive mapping that is
that
not.
doesn't work.
Yeah.
That will go to infinity.
Yeah.
No, this already ensures that you have a fixed point.
Okay.
And here I'm assuming that priority. And if it is bounded, it should have. So take kappa, this, then let's define tau n as the sum of alpha k1 minus alpha k. And by assumption, this is going to infinity. And define sigma of y this function, the minimum, forget about the minimum, is 1 over square root of pi y. Then, by analyzing this recursive optimal transport problem, you can prove explicitly, more explicit bound. You can get that this norm is less or equal. The residual after n iterations is less or equal than the kappa, the 2 times the distance to the fixed point, divided by square root of pi tau n. And you could think that pi is why pi appears here. It's a mysterious. What I can tell you is that you cannot improve. Pi is the best you can expect for that bound. If you give me anything smaller than 1 over square root of pi, I can build you an example that violates this equality.
This was any norm or the Euclidean?
Any norm.
And the pi still, it's weird. I mean, it's
Yeah.
Euclidean, you can see the pi showing up, but
When it comes out from the analysis, when the analysis is a bit involved because you reinterpret your z, the optimal transport. Well, first, you take your optimal transport. You bound it by a suboptimal transport, a very special one. This suboptimal transport, you reinterpret it as a transition probability for a Markov chain, which has nothing to do with the Markovian decision problem. It's a Markov chain in z, in n squared. And when you analyze this, you boil down to the gambler's ruin. You go, you ask the probabilities of what estimate you can give for the gambler's ruin. You end up with a function which is the Gauss hypergeometric function. You have these bounds in terms of this special function, and that special function gives you rise to 1 over square root of pi. So it's not about normal distribution, that's what one would expect. No, it's not that. It's a bit more involved. It comes from a probabilistic analysis, which was not obvious at the beginning. You have this recursive optimal transport. You take something which is suboptimal, that you reinterpret as a Markov chain, gives you gambler's ruin, and eventually gives you very explicit bounds. And what's interesting is that you cannot improve that bound, except you did a lot of majorization, but the majorizations somehow are not overstated. This bound is tight. You cannot improve. This we proved with Mario Bravo. Okay, in particular, you can have, if tau n goes to infinity, then the residual goes to 0, of course, 1 over square root, and it tells you what the speed is, 1 over square root of tau n. You already got. But this, of course, was for the deterministic case. There is no noise here. So what about if I introduce noise? So first, you can say, let's introduce some error En, but suppose that I can control this error. It's not a stochastic noise, but it's some, let's say, precision. I compute the operator T, and I have an error En that it's under my control. Well, it turns out that this bound that I have here, you see, this bound in this equation, it will still be there, but there should be some extra account for the errors. And here's the ugly expression. So you have your sigma tau n as before, and here you have the errors. Of course, if the error is 0, if the ek and en plus 1 are 0, it's the same as before. Otherwise, you have here a sort of convolution in the term in between. It's ugly. I don't expect you to interpret or to retain this, but you have some bound that you can control. Except that this requires En to be controlled. For instance, if I take En such that the sum is somehow controlled, then I can prove that the sequence still converges. So, okay, here are some examples of speeds of convergence for different controls of the errors. My only point here, don't look at the equations. Maybe if you're interested, you can look at it later. My point is that these bounds really can be used and translated into not only rates of convergence, but I can give you explicit bounds. This is less or equal than log tau n divided by square root of tau n multiplied by this constant. So you can really exploit this very precisely. So, okay, so here is the basic tool, a Markov chain with rewards, but I will skip that. I'm running out of time, so let me skip this. And so let's go back to stochastic AM and eventually come back to stochastic gradient descent and Markov decision process. How all of this applies? Well, by iteration is of this form. Now UN is an error, but which is not controlled. It's a stochastic term. If I want to apply my previous bound that we obtained previously, well, it will require that the noise goes to 0, almost surely, or something like this. And moreover, that this sum of alpha k norm u k is finite, but since the sum of alpha k is divergent, this requires that UK converges to 0 fast enough. And unfortunately, UK is not under my control. It's a stochastic. If I have a normal noise, well, I cannot expect something like this, not even in expectation. It's very restrictive, this. So the trick is to modify SKM and interpret an average iteration. 4 minutes. So let me just skip. There is some trick to replace UN by a sort of average noise, and then you have much better chances that this average noise comes to 0. And everything is controlled in terms of the variance. And finally, you can get convergence under some control on the variances, but maybe it's more meaningful. You get explicit error bounds as before in terms of controlling the variances. That becomes a bit technical, but it's the same ideas that you just adapt them over and over. So if you go to Q-learning, so here's I don't need to recall that this was the setting. You have operator H, which is non-expansive, blah, blah, blah. Here's the iterations that we propose. It's exactly the form of the KM. And by using this methodology developed in terms of optimal transport, you get this. So take alpha n, you're averaging as a power, then almost surely f of qn. Remember, the f was replacing the r bar. Well, in fact, it will converge to r bar. Also, the trajectory qn will converge to the optimal solution in norm infinity. Well, every norm is equivalent, so it doesn't matter. Qn converges to this q star, which is the unique solution of fq star equal r bar. And moreover, there is an explicit constant, this you have to look at the paper, such that the fixed point error is bounded by kappa a divided by square root of tau n. This gives you the rates of convergence. So I think I can stop there. If you're interested, we can later discuss how this applies also to stochastic gradient descent and how it recovers even pretty recent results from last year. But it recovers it from a technique which doesn't have to do with optimization or anything. It's just fixed point iterations. And for your question, once you have the Q star or any good enough approximation, you derive the optimal policy by saying, for each state, I look at what is the optimal action. What remains to do is what you said. What do I do when I don't have the possibility to resample? And I have only one path observation. We are working on that with Mario and with Ziliotto, Bruno, French colleague. He's coming to Santiago next week, in a couple of weeks. And we hope to finish that. So we expect to have news within next months. So at the end of this year, maybe we can say something. We do not expect. This is already slow. So we do not expect that this online will be faster. For sure not. And but then there are many variants. So this is one possibility. There are many variants with model reduction. So there's still a lot to do. But the take-home message for me would be that since we're talking about all of this, is basically concerned with computing, independent of the iterations that you do. You're trying to compute a fixed point of a non-expansive map. And non-expansivity is with respect to a bad norm, the norm infinity. So when you think of that, there is this technique based on optimal transport that might be useful. That's a take-home message. Keep in mind that you can estimate this by, and the mathematics is very nice. I've learned a lot of combinatorics and special functions and probability. That's it. Thank you very much.
Thank you, Roberto.
Oh, thank you. Let's have a coffee.
Yes.